Hey guys, I hope it's going well. This is our final lesson of the year, and it's can be conceptually tricky one, but I'm sure you'll be fine with it. It's kind of an intersection between normal distributions and the beginning of what you can do with that in terms of discrete data and probability, back to probabilities. And so first thing is one thing we've talked about quite a few times, which is the difference between discrete data and continuous data. So thus far in this unit, we've been talking about continuous types of data situations. So where data can take on an infinite number of values, and it's always things like, for example, things you can measure down to a smaller unit. So things like length of time, so how long it takes to tie your shoes, or if you measured something like your feet, you can always measure it down to a smaller number. But in discrete data, it's just data that are whole numbers. So things like the number of students in our class. So you can't have fractions of students or decimal versions of them. And so also the sum of two dice, for example, if we rolled two dice and added those numbers together, so 2, 3, 4, all the way to 12, you don't have anything in between those numbers. So what's amazing is that some discrete data situations actually fit the normal distribution. So I'm just going to write that down. Some discrete data distributions fit the normal distribution. And as we learned, because you can describe the normal distribution by its mean and the standard deviation, you can do all kinds of predictions about probabilities when they fall within that normal distribution. So the problem here with discrete data situations, if we take this example where, let's say I flipped a coin 20 times and I graphed the number of heads, what you would find in terms of theoretical probability is that it's most likely you would get heads 10 times. That makes sense. It's 50% of the time you would get heads. But it's possible you could get 9, 8, all the way down, but it becomes very unlikely to get anything close to, imagine you get 20 heads out of 20 tosses. It's very unlikely that's going to happen. And so the probability, if I measured that, would be very, very small, although it is theoretically possible. And so in these discrete data situations, it's great you can use the normal distribution, but the problem is that it's not actually continuous. So if you think about the number of, let's say we rolled 8 heads or flipped 8 heads, really, if you look at the graph here, I've included a line that goes along through, but really 8 we have to think of as a unit interval. And the unit interval, it helps us to approximate this because really there's a gap here under that line, and then we've gone over the line on this little portion. And so discrete data, you have to do some sort of approximation. So like, let's say I was to find the probability of 8 heads. What I actually need to do is to use the lower unit interval of 7.5 to the upper one of 8.5. And so in discrete data situations, you have to use what's called the unit interval. And the idea is because the area under the curve, like right here, there's this gap, and here I'm over top of it. And so I have to try to approximate that. So in order to account for this approximating the discrete numbers and try and make it a continuous normal distribution, we use what's called the continuity correction. And so if you know the situation's a normal distribution with discrete data, then you have to apply this continuity correction. For example, if we take what we have there with the number of heads and 20 tosses, if I was to say what's the probability of being less than 6, so instead of being right at 6, like here, I have to take the lower unit from 6. So we think of 6 between 5.5 and 6.5. And so really I'm taking it from here, and it's less than this. So going this way. So it's really, in terms of a calculation, less than 5.5. And this allows us to correct the fact that this is a discrete situation. And it is only an approximation. It's not perfect, but it's better than just saying the probability of 6. And it does make a difference in terms of the calculations. So in stats, we use that kind of thing. So if I said the probability of greater than 6 and it's discrete, I need to use the upper limit of a unit. And so it's 6.5. So somewhere here and going up like that. And then if I was to take the probability of 6, I have to think about it as its unit. So between 5.5 and 6.5. It's kind of like you're accounting for that bar in the bar graph. So I've got from 5.5 to 6.5. And it does create a little bit more work, but it's the way we can approximate discrete data into a continuous situation. So here's a really basic example. It says for a given discrete data set, and we assuming it fits the normal distribution, let's say it has a mean of 5 and a standard deviation of 1. So if I wanted to solve the probability of less than 3, knowing that it is discrete, really this should be the probability of x is less than the lower limit of that unit of 2.5. So in doing that, I know that my x value is 2.5. My mean we said in the question is 5, and my standard deviation is 1. So just like any normal distribution situation, I use the z-score. So remember the formula for the z-score, we use lots. And so I've got 2.5 minus the mean over the standard deviation. So this tells me the number of standard deviations above or below the mean. And so I get negative 2.5, which indicates it's below the mean. And so if you imagine that on this graph here, so my mean is the middle. So that's 5, 1 standard deviation, 2 standard deviations, 3 standard deviations below. So because my standard deviation is just 1, that makes these easy to calculate. So this is minus 2.5 below the mean. So that's right here. So what we can do, remember, just to relate this back to the normal distribution, is that we can use the z-score table. And so you go to your z-score table and you look up negative 2.5 and find the corresponding value, and you find that 0.062. And I've shown that quite a few times, so I'm not going to keep doing it. What that tells us is that this area here to the left of that point corresponds to 0.0062 or 0.62%. Like that. And so that's what we found. And that process isn't new, but just adding the continuity correction is. So we could have another situation where we say it's probability greater than 3. So in that case, its probability x is greater than 3.5 because it's not including 3. And so again, using my z-score, plug everything in, and I get minus 1.5. So that corresponds to a value 1.5 standard deviations below the mean. So my z-score in this case corresponds to 0.0668. And you can try that on your calculator. So that gives us this point here. So this is 1.5 standard deviations below the mean, where my x value is 3.5. This 0.0668 corresponds to everything to the left side of that point. But because we're looking for greater than 3, or 3.5, I want everything to the right side of that. So I want everything over here. So greater than that guy. So what I need to do is just do a simple 1 minus 0.0668. And again, we've done that kind of thing before, but just to remind you, so you get 0.9332. And that's the probability or the percent of data that fall above that point. So the majority of that data. So the last one here says the probability of exactly 3. So we use the unit, which is 2.5 is less than x, which is less than 3.5. And we take what we've already got because we've already calculated these. So I need the upper limit first because it's the bigger number, and I subtract. So I get the difference between them. And so my lower limit my upper limit rather comes from this 0.0668. And the other one here was this 0.0062. And that tells me the difference between, which is going to correspond, and I'll highlight in a second. So this becomes 0.0606 or 6.06%. And that, pick a different color, so this guy corresponds to this. So between 2.5 and 3.5, that's the percent that I get, or my probability, whichever way you want to think of it. So again, a bit confusing in terms of conceptual stuff, but kind of makes sense in the end. So let's try an example here where you can use this. So we've got a company produces boxes of candy-coated chocolate pieces. The number of pieces in each box is assumed to be normally distributed with a mean of 48 pieces and a standard deviation of 4.3 pieces. Quality control will reject any box fewer than 44 pieces, and boxes with 55 or more will result in excess cost to the company. So the first question says, does this situation have discrete or continuous data? Assuming the pieces are whole, so whole pieces of candy, that means it's discrete. And somebody might say, well, the standard deviation is 4.3, but that's just the average deviation away from the mean. Because you often, if you take the average of something, like if you have a whole bunch of points and you average them out, you're going to get fraction. It doesn't mean that you have a continuous situation. So we've got a discrete data, so we have to treat it like that. So the second question says, what's the probability that a box selected at random contains exactly 50 pieces? So knowing it's discrete, I have to think of it really between 49.5 and 50.5. And this concept, once you get it here, it's easy, I think, but it's that you have to remember every time you reach this discrete data situation, you've got to apply this. And that's what becomes tricky. So if I write down the things I know, I've got my point, 49.5, but I've got to also do it for 50.5. That's kind of a pain because you got to two separate calculations with the z-score, but that's what we have to do for discrete data. My mean is going to be the same in both, which was given in the question, which is 48. My standard deviation is 4.3 pieces, like that. So I take my z-score and I plug these things in. I'll just rewrite the z-score one more time. Plug these things in. And I get z-score of 0.35 standard deviations above the mean because it's positive. And I do the same thing here with 50.5. And I get, 0.58. So you go to your z-score table, you translate those over. That becomes 0.6368. This guy becomes 0.7190. So in the end, the probability of being exactly 50 is the difference between those, bigger one minus the smaller one. So we get 0.0822, therefore the probability of 50 pieces is approximately 8.22%, like that. The next one says, what percent of the production will be rejected by quality control as containing too few pieces? So if we go back to the question, that's this part here. The quality control will reject any box fewer than 44. So anything below 44. So fewer than means less than. So we don't include 44. Because of that, this becomes x is less than 43.5. And again, because it's discrete. So I plug that in just like we did before, so we kind of get a repetitive process. I get negative 1.05 standard deviations, or 1.05 standard deviations below. And that gives me a z-score if you look that up. And I would recommend trying that. Oops. 6.9. So you get approximately 14.69% will be rejected because they don't have enough candies in the box, and therefore they don't meet those guidelines. The next one says, if each machine produces 130,000 boxes per shift, how many of these will lie within the acceptable range? So the range, the lower limit, we already established, is less than 44, I should say. And then in the question, I think it says boxes with 55 or more, so it can include result in excess costs. So the upper limit, it's greater than or equal to 55. So we have to think about how that translates into our continuity correction. So I know I've got a lower limit of less than 44, so 43.5. And then it can include 55, so I have to take the whole full unit of 55, and I say 54.5 like that. And so again, I've got two separate calculations for my z-score to make. We've already done one of them. That's the 43.5 on the previous page. So I'll just write that in. And then the other one we have to calculate 54.5. That one comes out to approximately 1.51. Z-score then of 0.9345. And so my probability between each of those, 54.5, is I take the upper limit minus the lower limit. And you get 0.7876. So what that means is that 78.76% of the boxes produced are accepted, are within the accepted range. So therefore, in 130,000, I just take 130,000 and I multiply it by that percentage. And that works out to 102,388. And so therefore, in a shift, 102,388 are accepted. So really not that many, like we're only accepting 78%. A lot are being rejected because they don't fit. So if you own this company, what conclusions might you reach about your production process? Really, therefore, too many are rejected. And they need to reduce then the standard deviation. So they need to reduce the differences between each package of chocolates. And then they'll get more acceptance. Okay, the end. That's the end of this unit, the end of this course. Practice questions for this topic are here. It's not too many. You should get through it pretty quick. And the answers are below on the same page. All right. Take care, guys. Let me know if you have any questions.